Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to week 4, lecture 1, dynamic atomic force microscopy methods. In the last lecture, we were talking about VEDA simulations, a virtual environment for dynamic AFM, and we went through a lot of background on how you might be able to use it for simulating a lot of realistic situations, both for spectroscopy, where you approach the sample, as well as for scanning tools, and that you could use it both for frequency modulation as well as amplitude modulation methods of operation. This week we're going to focus on a slightly more advanced topic, which is that of force reconstruction. And following that in the last week, we'll move on to application areas where we're going to focus on electrostatic force microscopy, Kelvin force microscopy, AFM in liquids, and magnetic force microscopy. But this week is going to be dedicated to trying to understand mostly details of frequency modulated atomic force microscopy and how we could use that for reconstructing interaction forces between the tip and the sample. Now, what we refer to as force spectroscopy is really the process of converting the observables in an AFM experiment into the tip sample interaction force as a function of the gap d. In the case of static AFM, that's one way to do this. The observables are the cantilever deflection as a function of z, and we've already talked about in part 1 of the class how you might use that to actually get interaction force as a function of gap d. We talked about also the fact that there are challenges in that you can't access the entire f versus d curve, and so on. On the other hand, dynamic atomic force microscopy methods use a resonant oscillating probe tip, and the observables are very different. For example, in the case of frequency modulated AFM, we're going to be using the frequency shift and the excitation signal as a function of z as you approach the sample to reconstruct and to be able to figure out, what are the interaction forces F as a function of the gap D. In the case of tapping mode, or amplitude modulated AFM as you approach a sample, the amplitude and the phase are the observables, and the change as you approach the sample as a function of z. And so the question would come up, how would you convert that information into F versus D? This whole field is sometimes called dynamic force spectroscopy, which is the use of dynamic AFM for force spectroscopy. I do want to point out that throughout this class we've been focusing and talking about frequency modulated AFM in the context of two different feedback loops, one which is a phase lock loop and the other one which changes the excitation to keep the oscillation amplitude constant. In reality, there are more than one ways of implementing FM-AFM. There is another one which is, based on a positive feedback system, which basically is able to drive the probe you're using into a self-excited state of oscillation. We're not going to be talking of that method of implementing FM-AFM in this particular class, but references are provided at the end of this lecture for you to look up details of that method. All right, so using the method that we have discussed in the class, you may recall that when you're approaching a sample, we're going to be tracking frequency shift F0 prime, which is the new frequency, the modified frequency, due to the tip sample interaction forces as a function of z, and you might expect a graph like shown on the left here, that as you approach the sample, the attractive forces make the frequency shift become negative, or the modified frequency becomes lesser than the natural frequency of the probe, and then as repulsive interactions set in, the modified natural frequency of the probe, which is F0 prime, I think we'll also call it effective natural frequency of the probe. It starts increasing as you come much closer to the sample due to the repulsive interactions. In the meantime, the excitation force has to increase to keep the oscillation amplitude constant. And we derived relationships between the modified effective frequency of the probe, and the virial, which codifies within it the effect of the conservative tip-sample interaction forces. We also came up with the link between the excitation amplitude F0 and the dissipative tip-sample interaction, which is given by the term E sub Ts. So really, these are the observables we have in FM-AFM as you approach a sample. The question is, clearly, frequency shift is going to be related to the conservative interactions, and the excitation versus Z is going to be connected to dissipative interactions. But how does one take this relationship, these observables as a function of Z, and convert them into the actual tip-sample interaction forces? In the case of frequency shifts, we'll be looking at reconstructing the conservative part of the tip-sample interaction force. In the case of the excitation versus Z, we're going to be looking to reconstruct the dissipative part of the interaction force. So we're going to be talking about this for the next 3 or 4 lectures in some detail. Now, let us begin by trying to understand the frequency shift and how it's related to the conservative part of the interaction. And as we've already seen in the previous slide, that F0 prime depends just on the conservative part. So why don't we begin this discussion by looking at the point mass oscillator coupled to the interaction forces, but in the absence of any dissipative interactions and in the absence of any excitation. So we're just going to basically look at this oscillating probe interacting with the sample and just try to understand what are the natural frequencies and how they depend on Z, how they depend on the oscillation amplitude you choose to oscillate the probe at. In light of that, we take the equation that we've been dealing with before, which is a point mass oscillator model, equation 1, but we don't have any excitation included in it, and we don't have any dissipation or damping or Q factor included in it. That being the case, the interaction force is purely conservative, which means it only depends on the tip sample gap D. Whenever there's an interaction force that depends only on the tip position, D or Q, then it means that it can be represented as the gradient in terms of the gradient of a potential energy function. In this case, we call it U sub Ts. U sub Ts is the potential energy due to the tip interacting with the substrate. You can think about it in the following manner, that if the tip were really pushing deeply into the surface, then there is some potential energy in the system, because if you leave the tip alone, what would happen is the surface would try to eject the tip. And so you can convert some of this stored tip sample energy into useful work if needed. So U sub Ts is going to be the potential energy associated with the interaction, and negative of the gradient of that potential energy is going to give you the tip sample interaction force. In other words, you can also invert this relationship and look at the tip sample interaction force under the integral as shown just below equation 2, where we now write the potential energy at infinity minus the potential energy at some gap D must equal negative of the work done by the interaction forces in moving the tip from D all the way to infinity. We, of course, will define the potential energy, tip sample potential energy, to be 0 when the gap is infinity. As a result, we come up with equation 3 that tells us the relationship between the potential energy of the tip located at a gap D and the conservative interaction forces between the tip and the sample. Now, what I've done on the right is give you an example of a tip sample interaction force versus D and the corresponding potential energy function associated with it. The corresponding potential energy function associated with it is given in terms of electron volts. The reason we choose to do it is because electron volts is a very often used unit for energy dissipation and understanding really tip sample interaction energies in dynamic AFM. I would argue that it's the unit of choice in this case. So an electron volt is basically 1.602 times 10 to the minus 19 joules, for those of you who are inclined to work thinking about joules. So we have, in terms of electron volts, the potential energy corresponding to this tip sample interaction force model. The details of the model used for this graph are again shown in the appendix, but the thing I want to bring to your attention is that the tip sample interaction force is the gradient of the potential energy function. So whenever the tip sample interaction force becomes 0, the gradient of the potential energy becomes 0. In other words, F equal to 0 corresponds to a minimum in the potential energy. As you can see in the red curve, when the red curve, which is the force versus distance, when that becomes 0, the potential energy, which is the green curve, reaches its local minimum, i.e. the gradient of the potential energy becomes 0 at that point. All right. Now, another important result we can deduce, and the details are in the appendix, is that the equation 1 that we wrote out, which is the tip sample oscillation equation, can actually be rewritten or can be thought of as being a statement of the conservation of energy. Why is energy conserved in the system? Because there's no dissipation, right? There's just inertial forces, and there's just a conservative interaction force. So if you look up the appendix, you'll see why equation 1 is simply a restatement of the conservation of energy principle. In this particular case, the total energy of the probe oscillator system can be thought about as comprised into two parts. The kinetic energy of the point mass, which is going to be given by 1/2 m q dot squared, which is the kinetic energy of the particle, or of the point mass. The potential energy now is going to consist of two pieces. One is going to be the potential energy stored in the spring of the point mass oscillator, but also is going to be some potential energy stored in the tip sample interaction force. The total potential energy is going to be U sub total, and that can be written as a combination of these two potential energies. It can be written in terms of Q, which is the tip displacement from its mean position, or it can be written in terms of D, which is the absolute gap between the tip and the sample. Either way, at the end of the day, when one takes this total potential energy into account, you can show that the equation of motion that was derived, equation 1, is simply a statement of the following equation, which is 4, which is that mq double dot equals the derivative or the gradient of the potential energy with respect to q, or with respect to d if you write the equation in terms of d. Which really brings us to a very important conclusion, which is that when you're looking at understanding frequency shifts and how they're related to, tip sample interaction forces, you can think of this problem in the context of a more classical problem in physics, which is that of the oscillations of a point mass in a potential well, in a potential energy well. So the big question here to think about is, what is the potential energy well we're talking about? So to make that a little clearer, I have tried to provide you an example here. This, again, is an example where all the details and the parameters used for this example are shown in the appendix. But basically, we've taken a cantilever probe with a K of 15 Newton per meter, and there is a potential energy function of the form that's shown here. This is a potential energy function that's actually derived from a Leonard-Jones potential. It's given in terms of electron volts as shown, and the total energy then simply is going to be a combination of the tip sample UTS potential energy plus the cantilever potential energy. What I want to highlight for you is that the potential energy of the cantilever depends on the location Z, because the deflection of the spring is simply going to be Z minus D. And so when you write down the total potential energy as a function of D, Z does come in explicitly into the total energy expression. So really, if you think about what we're trying to do, we're trying to sum together the total potential energy, U total, as a sum of the cantilever potential energy plus the tip sample interaction energy. And I've graphed those two. In blue, what you see is the tip sample potential energy as a function of D. We're going to add that to the cantilever potential energy, which is shown below. Now, again, keep in mind that the cantilever potential energy is simply a quadratic, just shows a quadratic dependence on Q minus Z minus Q, or in other words, Z minus D the whole squared. In other words, a quadratic dependence on the compression or elongation of the spring. The key thing is when you're going to add these two together, the resulting curve is going to depend on what z is chosen, right? And I've tried to illustrate this by drawing the total potential energy for 3 values of z for this particular interaction well on the right. What you see on the right, when you do z equal to 3, you find that z is a bit far from 0, and so the quadratic potential well of the oscillator has a chance to really increase in magnitude. And then at the very left edge, you see that the tip sample potential energy is able to gently perturb the otherwise quadratic dependence of that interaction potential well. On the other hand, as you come closer to the surface, z equal to 2, you find that the potential energy well, due to the cantilever, doesn't have time to increase too much in height, so that the potential energy due to the attractive interaction forces, the repulsive interaction forces, are able to modify it. When you come very close to the sample, z equal to 1 nanometer, you actually find that the effect of the tip sample interaction forces on modifying the overall potential is very substantial. In fact, you actually create another equilibrium position, another minimum of the potential energy. So at very small gaps, you actually have 2 different wells in the energy landscape here. The 2 main conclusions as you see this is that as one approaches the sample, 2 things are happening. If you think about this well where your probe is going to oscillate, its curvature is gently changing as you approach the sample. And then the second thing that happens is that at some point you create another local minimum which is a very sharp curvature associated with it. So those are 2 things that are going to keep happening, and we will keep them in mind as we move forward to understanding how to relate these changes in shapes of the potential energy landscape to the frequency shifts that you would observe. So we begin with a simple case, which is that of a quadratic potential well. So let us assume that the tip sample interaction potential is 0, and that the total potential energy is simply given by the quadratic potential of the elastic energy stored in the point mass model, 1/2 kq squared, which is sketched on the left. What's going to happen is, if you imagine this potential well, if you were to take a ball, started off a certain height, and let it go, it would roll and go up to the same height on the other side of the well and turn around, go all the way back up, and it would keep oscillating like that forever since there's no dissipation. In effect, what's happening is the total energy of this oscillator is decided by the initial height that you give to this ball, because when you release the ball, the kinetic energy is going to be 0. By the time it reaches the bottom of the well, all the potential energies got converted to kinetic energy, and then it keeps rolling back up to the same height, converting all the kinetic energy once more into potential energy, and the process keeps repeating itself. Now, you can look up the appendix for some more details, but when you have a potential like this, 2 important things happen out of it. First of all, the solution for the equation of motion is going to be simply a pure sine wave, whose frequency is given by 1/2 pi square root k over m, which is a known result. Now, there are 2 important conclusions that I mentioned here. The first is that the natural frequency of oscillation in this well depends on k, square root k over m. If you think about what k really means, k is of course the equivalent stiffness of the point mass oscillator, but in the context of the energy well, remember the shape of this well is 1/2 kq squared, so k can be thought of as being the curvature of the well. So the frequency of the oscillator is going to first depend on the curvature of the well. The sharper the curvature of the well is, the higher the K is going to be, and the higher the frequency is going to be. The shallower the well is, the lower the K is, and the lower the natural frequency is going to be. The second conclusion that comes out of it is that when you have a purely quadratic interaction potential well, or purely quadratic potential energy landscape, the frequency is independent of the oscillation amplitude. So that comes out of the solution of the problem. But basically, when you have this quadratic well, it doesn't matter how high you start it. the frequency and the time period are going to remain exactly the same. So this is what's called an isochronous kind of oscillator. Now, to give you an idea about what is the total energy, potential energy we're talking about in typical AFM probes, what I've plotted out here is a measure of the energy, total maximum energy, potential energy contained in an oscillator, which is U cant, as a function of the initial displacement Q in nanometers for various kinds of cantilever stiffnesses, ranging from very soft to very stiff. What's really interesting is, I like this example very much because it tells you that most oscillators that we use for AFM, when you look at the maximum potential energy, which is the potential energy corresponding to when the tip is at an extreme position, tends to be somewhere between 100 to 10,000 electron volts. This is very typical. So it gives you a very important idea as to what is the potential energy typically, maximum potential energy contained in an oscillating AFM probe. In contrast, the tip sample interaction potential energy is typically going to be of the order of 1 to 10 electron volts. So tip sample interaction potential energy is usually 100th to 1000th, maybe less of the maximum potential energy contained in the oscillator. And this forms the basis for the entire theory of frequency modulated AFM, which allows us to bring methods from perturbation theory to apply to frequency modulated AFM. All right, so what if we change this interaction potential and we make it, add another term to it, a quartic term to it? Now, when you add a quartic term to it and look at the equation of motion, in addition to the KQ term in the equation of motion, now you have a alpha Q cubed term as well. You can try to solve this by doing a simple expansion in terms of sines and cosines. Again, the details are shown in the appendix. What transpires at the end of it is that the influence of adding this additional term has been to really change the shape of the well. The well remains symmetric, but it's no longer quadratic. It's a little steeper in some sense. The second important result that comes out of it is that the natural frequency now is going to depend on the oscillation amplitude, in this case, which is B1. This is the first time we've been seeing this, we've seen this, that the natural frequency now starts to depend on the oscillation amplitude. On the bottom right, I've given you an example in this particular case for how the natural frequency would change as a function of the oscillator amplitude. Now, if we choose another perturbation and choose to add a cubic term in the potential energy function, what it tends to do is to take this potential energy landscape you had and make it perturb it asymmetrically. If you look at the details in this slide and in the appendix, you will notice that the effect of this asymmetric perturbation is also to change the natural frequency of the probe. And again, the natural frequency of the probe continues to depend on the amplitude of the oscillator. But importantly, there's also now the A naught term in this in the Fourier series expansion that you see out here is no longer zero. So there's going to be the solution will or the equilibrium position of the tip will actually move a little bit from where it was before. So put together, we again generally find that as soon as you perturb the interaction, the quadratic interaction potential with terms that come from the tip sample interaction potential, we expect to see a shift in the mean position of the tip. We expect to see a change in the natural frequency because the curvature changes, but we also expect to see an amplitude dependence of the natural frequency. All put together, if we were to go back to the problem I started working out at the start of this class, where we had written out a potential energy expression, what I've done in this case is now to plot the potential energy landscape as a function of z, starting at z equal to 2 and going all the way down to 0.2. And so I'm just going to go to the board and discuss that a little better in some detail. What I've chosen to do here is to plot the total potential energy function for 3 different values of z. When you're a little further from the sample at 2, z equal to 1, z equal to 0.2. And in each of these situations, we have to imagine rolling a ball in each one of them. So if you were to take a ball here and roll it down, it would oscillate with a certain frequency, right? When Z comes closer to the sample, you find that the potential energy well becomes more shallow. And if you release the ball here and let it go, you would find that its oscillation frequency actually starts decreasing due to the effect of the attractive forces that perturb this well, that kind of make the well a little more shallow. In the final case, when Z becomes very, very small in this particular model, we are left with just one interaction potential. If you were to take a ball and roll it down here, you would imagine that it's a very sharp well, so the natural frequency would become very high again. So what we expect to see in this transition as we change Z and start decreasing it is natural frequency should decrease a little first, and then it should start increasing as it goes into that very sharp well. And I've sketched that out for you here, is how we expect the natural frequency shift to change as a function of Z. As you approach a sample, frequency shift should become negative first, become positive again. And it should also depend on the oscillation amplitude, in the sense that large oscillation amplitudes will tend to minimize the effect of the attractive forces. And small oscillation amplitudes will sort of amplify and make much more clear the effect of the attractive forces. Thank you very much.